Okay, where were we? So just quickly be reminded of what methods we have covered. Okay, so last time we went through the Jupyter notebook, but we didn't really get down any annotations in our notes. But just remember that we were talking about these methods that also start and end with underscores, right? So basically, the first one is the string, which is telling basically the print operation. What does it print for your object, right? And then for LT, that's actually less than. So whenever you think about the comparison between your objects, then that LT function is well a method that just compares the a pair of objects. All right. And then we have the subclass. All right. So basically, for a sports car within the class of car, it's just gonna be the subclass with the bracket calling the superclass. Mm, and yeah, so that's the polymorphism, which is essentially just one formula of many forms. So they are utilizing many forms. So for different subclass, so one scenario is that there will be different possible utilization of methods. Okay, so the methods may be defined explicitly in different ways. But then let's say for different classes that you can have different ways to compute, let's say lesson the inequality less than, okay, as a Boolean operation. So those are the things that about OOP. And now we're talking about data structures, basically implementing special data structures that are sort of you're able to program them using OOP. Okay, so we were talking about stacks. So one example is for this kind of edits, right? So I can do undo and redo. Let's say I put 1, 2, 3, 4, 5. So upon doing undo, it's going to always be the last operation that I can also sequentially redo them. So that's one example that we talk about. But in fact, we do have examples that just it's very important, but sometimes we just sort of forget that kind of applications. So stacks, remember this is always the last in first out. So basically, you have a sequence of objects, but you can always start with the last one. So when does that happen? That can happen when you have compositions. So this is essentially very important in terms of, let's say, compositional structure, especially let's say for multi-layer neural nets. So it's going to be a huge composition. So to put it a little bit more explicitly, we have, let's say, xn equal, so it's going to be the last operation. It's going to be the final output, and we have an input of x0. So this is, let's say, f1 composed with f2 composes all the way down to, let's say, fn of x0. Right? So we have a sequence of functions. You specify, usually this is the way that you do it. It's going to be f1, f2, all the way down to fn, but the inners are having the larger indices. Okay, the inners are the in the natural way of thinking about this notation is going to be the larger indices are more inner. So when you think about this kind of mapping, essentially you have what you have x0 using fn maps you to f1 x1, and then you're using fn minus 1 that will map you to x2, and it just continues. So this is fn minus 2 all the way down to the last one. So just remember what are special here. Excuse me. What are special here? I want to basically the indices they add to n, right, everywhere right here. Okay, so you start with f2, you map using fn minus 2, so the indices they add to n. So finally you want to get to using f1, so that's actually what, that's actually xn minus 1, and finally you get to xn. Okay, So this is the scenario where you must utilize the stack storage, because essentially what are you storing? You're storing as a functional. Okay, you have a sequence of functions. You have f1 through fn as the elements in the stack. So when you're doing the evaluation, you are moving out the last one composed with your current vector. So it's always going to be fn. Uh, okay, so evaluation fn x on x0, and then fn minus 1 x on the computed output x1. And then that will give you the new output x2, and you put it into fn minus 2. So it's going to be sort of like the backwards kind of computational order. Okay, so it's from the last one in the list all the way up. Okay, so that's basically saying I'm popping every time the last element of my stack. So basically, like the if I have a stack of papers, it's always the top piece that I can handle, and then I do the composition. I do the evaluation, and then I take out the next, second last piece of paper, and then work on the evaluation all the way down to the bottom. Okay, so this is the forward pass. So basically, evaluating the final output of the composition. And then if you think about the back what's that word? Um, the backtracking of the gradient. Okay, if you want to take the derivative, so using the chain rule, you also have to do this same procedure, which is why here I'm now talking about this everything here really explicitly. So far for the forward pass, makes sense now? So the forward pass is saying, okay, I have x0, the initial input, I want to compose using f1 all the way through fn, but unfortunately I have to deal with the inner functions first. Okay, the inner functions have the larger indices. Okay, fn minus 1 all the way up to the most outer, which is f1. Okay. Yeah, right. And then let's say if you want to change things, right? So if you want to change the elements, you still have to peel from the most inner one all the way to the outer. So which is exactly why you only want to change the most inner, or you want to add in some inner functions, or remove certain inner functions. If basically that's basically you do have an order that you need to sort of preserve. So basically you have a list, and then okay, when you're doing the computation, it's always from the inner to the outer. So that's every time remove one function, evaluate on that, and then move on. Okay, so that's yeah, adding and removing. Um, So now let's also talk about the back propagation. Well, which is essentially what? Essentially calculating the derivative. Okay, so the derivative. Just remember these vectors. Okay, these vectors later. Well, if you have taken 500, that's good. If not, you will see that in 500 near the end of the semester talking about the chain rule. So essentially, what you're what you're dealing with is x0, x1, xn. They are all multivariate, just basically vectors. Okay, so you have vectors, then each function they are essentially mapping a vector to possibly a vector of another dimension. Then when you talk about the chain rule, okay, it's going to be the Jacobian form. It's going to be the Jacobian of the whole composition. Let me just use the notation that let me think. The standard notation is let's say dx and dx0. So but here just although it's written like derivatives, but they are in the Jacobian sense. Okay, so it's in the Jacobian matrix. So basically, it's a matrix that has the partial derivatives that are in different columns. Okay, each column is with respect to one particular input. All right, I have xn. Let's say some vector of m dimensional. Then you will have m rows. X1, x0 has, let's say, n different arguments. Then the first argument is going to be the first column having m rows. The second one is the second column m rows all the way down to the nth column m rows. So it's going to be m rows n columns as a matrix. So that's well, in 500 they will explicitly talk about the chain rule. That's okay. This is going to be okay, it's going to be dxn minus 1 all the way dxn minus 1 dxn minus 2. So basically it's just going to be remember every layer it's a mapping from x0 to x1, x1 to x2. So these are all going to give you a relatively more straightforward Jacobian matrices. But the way to write it is still the traditional chain rule that you have seen in Calc 3. So xn, okay, all the way down. So it's going to be dx2, dx1, dx1, dx0. Okay, so it's going to be what? It's going to be n layers, right? And now, what are they? Just realize, I think we're running out of space. And let me put it here. Okay, let me put it here. And let me put this this part on the top. I don't want to move the page, but I want to move this. Let me be careful here. Okay, so it prevents me from moving that. Let me do this. Just be careful when you're trying to move certain text. Okay, that should be fine. Just make sure everything is aligned. Okay, good. All right, so okay. Now let's write it a little bit more explicitly. So this part is dxn minus 1. Where is it? It's actually here. I thought I sort of was hiding that. I felt it is okay. This is still necessary, so I move it a little bit higher. Okay, so basically, you're having the input xn minus 1 for the last layer, and you get to xn. Okay, so that function is f1. So essentially, if you want to write it in the function form, it's the, well, you can call it a derivative. Okay, it's the derivative of f1 evaluated at xn minus 1. Okay, so this is actually, so here we're doing the notation that's a little bit I'm trying to make it intuitive. Okay, so that's the derivative of xn minus 1. Essentially it's a matrix. All right, but then the next one is going to be what is f1. And then the next one is the one with a larger index, which is f2. So it's going to be the derivative of f2 evaluated at n minus 2. And all the way up. Okay, so now here at dx2 x1 is where is you have the input x1 and output x2 is actually this one. It's going to give you f n minus 1 prime. Okay, and then evaluate at x1. And finally, you need f prime. So which one is fn prime evaluated at x0. All right, so indeed it looks ugly, right? But now what's the idea? Usually in the computations, these derivatives, they are encoded in your program, right? But then if you want to do the computation, you do notice that, okay, your input is x0 right here. That's the input. Let me highlight. This is the input. And that's the output of the composition. So earlier when we talk about the forward pass, we were saying you have to compute x0, then x1, then x2, then all the way down to xn. So you need to go through this procedure of fn minus 1 all the way down through f1, this kind of evaluation, right? So that's the function evaluation. But now, in terms of the derivatives, okay, if you look at the inputs of these Jacobian uh, derivatives, okay, you need to plug in what? You need to plug in also all those vectors, x0, x1, x2, all the way up to xn minus 1. And it has to be done in also this kind of same order. So it's still from the inner to the outer. Okay. So this is sort of unfortunate. What I'm talking about right here is that okay, you're given x0, so you are able to compute this. But while you are doing this, you also need to compute x1, and later x2 will rely on x1. So which is the next step? And basically, like I said, xm minus 1 here is here, which relies on the prior computations of xm minus 2, which is this vector here. Okay, so it's also this kind of what I'm saying is again this order. Okay, so this is exactly why in the stack you are dealing with the elements with larger indices first, all the way to the left.
Professor,
Yes.
so in a matrix, the rows are inputs and the columns would be output if I consider it as a matrix.
Let me see. Uh, so yeah, let me just put it down. So to make it a little bit more explicit, but well, this is a topic from mostly emphasized in another course. But let's say I have F mapping from R. What did I just mention? I said M. Okay, m rows, n columns. Okay, so we have an m-dimensional vector that's we're mapping to n variables. What does it mean? It means, let's say we have f of x1. I'm using x. Okay, so let me use y. So it's going to be y1 all the way down through ym, mapping to a vector of n dimensions. Okay, so actually each one of them is going to be a multivariate function. Make sense?
Yeah, yeah.
Yeah, right. So basically, yeah. So we have n dimensions. Okay, each one of them is essentially a scalar valued function. But now they can depend on each of the arguments y1 through ym. Right. So here, what I'm talking about the Jacobian matrix is the following. So each component it will have a partial derivative. Okay, so basically what I'm saying here is that z1 can have partial derivatives with respect to y1, y2, all the way down through ym. And also all the way through the end, they also have this kind of property. So you just want to lay everything out in the matrix, which is in the form of this. Okay, so it's going to be the partial derivative of z1 with respect to y1, and I'm just differentiating every z component with respect to y1. I'm putting it in the first column, right? So that now this column has the same format of the output column, right? And then for the second column, I'm going to do the same. I'm just going to do the partial derivative of z1 through zn with respect to y2. And then finally, I'm gonna look at the last variable, which is which is ym, which is gonna be the m's column. Oh, I see. I sort of like swapped the order of variables when I was discussing, but you get the point. So here, basically, column-wise, you are not changing the structure, okay, of your output, but then each column deal with the partial derivative of a particular variable. It's going to be from y1 through OIM. So it's indeed a matrix, but if you look at the dimension, it's n by n. Okay. So n is basically how many rows are there, and m is how many inputs are there. It's just going to be now columns. How many columns?
Got it. Thank you, Professor.
Yeah, yeah. So yeah, this is something that if you are in the data science program, they would cover in 500, and they also will talk about it in 591 a little bit because 591 deals with um, various kinds of optimization problems. Okay, machine learning problems. And the chain rule actually is really important because essentially all the methods they handle using first order methods. Okay, this is computing the gradients. So they will have to utilize Jacobian chain rule in the sense. So okay, if this is good, then essentially what I have in underline double underline in purple, they are all just the Jacobian matrices. Okay. And so unfortunately, for this kind of derivative, okay, you do need to have a bunch of matrices multiplied. And what's the order? So you need to put it in a nice order. So you need to play with, let's say, f prime of f prime fm prime evaluated as x0, okay, first. And then you compute the one on the left, which is this one. Okay, so it's going to be from the ones with the larger indices all the way down to the ones with the smaller indices. So this is also the sense of a stack. So in general, if you have, let's say, a big composition of functions, then it's going to be f1 through fn, just like what we discussed. Okay, f1 is the most outer, fn is the most inner. So essentially, for the forward pass, when you evaluate function value, and for this backwards back propagation, you also have to sort of deal with this kind of fn prime, fn minus one prime, this kind of order. So that's this is a utilization of the stack data structure. So the last in, first out. Okay, so last meaning is actually more inner in the composition. That will be the first that you compute. So well, yeah, this is a data structure. I would say the logic, okay, because essentially, I would have to admit if you are programming the neural network, then you do not really have to set up a stack class. So it's a high level idea. Okay, so it's sort of like a one application that you sort of have to be careful when you're dealing with this stack data structure. But then, of course, basically whatever way that's more convenient for your code, that will be the better. So as an application, does it make sense now?
Yeah. So it's like primary focus application wise is like computing transformations if we're using Jacobian and derivatives.
Yeah, exactly. Yeah, for compositions, unfortunately, you have it's like an onion, but it's like an onion, but the outer layers are the outer functions. So it's kind of counterintuitive that you are actually looking at the inner part and going to the outside, which is what's happening right here.
So would stacks be like beneficial in forming like probability models in Python then? It uses like Jacobian and derivatives, and in theory, you could use a transformation to then help solve a probability model.
Yeah, right. So yeah, well, in 591, many of the topics, many of the machine learning models, essentially they are statistical machine learning models. So indeed, yeah, if I think about the question that you're asking, so essentially yes, you will have, in general, for machine learning, essentially you have a model, and then usually you have a prediction of some true false label, and then you are doing the prediction minus the true value, and then you take the square. So that's the mean squared error minimization. So that's the composition right there. So you have a model which possibly is a composition, but then you minus something and then take the square. That's another layer of composition. So that this kind of chain rule appears really often. Okay,
Yeah.
when you're setting things up, especially when you're coding things yourself. So so yeah, that appears a lot. Well, but on the other end, the more that you know about packages, then what's called the auto differentiation is basically saying, okay, now all the functions, all the building blocks of the models, they are coded and the derivatives are coded. So you can just call them in a nice way so that you don't have to hand code everything. But that's sort of like a more higher level understanding that you have to have, okay, to utilize certain packages. But yeah, that's those are the things that you can do in, let's say, PyTorch. So yeah. But yeah, this is like one example of stack. So you sort of utilize this kind of like a last in, first out. Just realize, okay, every last element within your stack is essentially the most inner layer. And once you toss that out, it's gonna be the second last. So exactly that's the way that you deal with, okay, when you are computing the compositional value and the derivative of that kind of composition. So it's always you handle those first, and then it's one at a time, okay, one at a time. So that's indeed. So yeah, on high level, even though you may not get a class for stacks, but that's indeed natural. You are essentially enforcing it when you are coding. All right. Okay, so these are stacks. And queues. Okay, okay, the queues we also talk about that. Okay, so those are the two we'll sort of emphasize within section 8. And later, when we get into the live coding session, there's gonna also be implementing stacks and queues. So let's now talk about the stacks. A stack is okay, it's a more dynamic version of a list. So, but basically, we can always utilize the list as a data type to encode our stack. But we just remember that we are not really manipulating all the things in the list. We are just manipulating the last the one with the largest index. So, and if we want to remove an item, we simply cross it out for at the end. Okay, so this is the every time we remove the last one. Yeah, with the stack, we insert and remove elements as that are pre specified, meaning the last one. Okay, I think we did this graph. So okay, we did this graph. So we will talk about that. Okay, if you push an element, it's always gonna at the end of your data structure, and then when you pop, you just pop the one with the at the end. Okay, so it's always that one. For the queue, it's kind of opposite. Okay, so when you have, let's say, indices from 0 all the way 1, 2, 3, 4, all the way 5, 6, 7, 8, 9, 10, 11. So essentially, the next one that you get in here is going to be the 12th. We will index 12, but then if you are dequeuing, okay, so if you want to remove an element, it's always going to be the zeros that's removed. So first come, first serve. But of course, you are able to sort of read what's going to be the rear, what's going to be the front. Okay, so the idea is essentially not very special, but what's special here are what can be changed, what cannot be changed. Okay, so in terms of a stack, you can only change the last element. So when you include a new element, it's going to be just now the last one within the stack. And then if you want to pop, okay, so you can only toss away the last. And then in terms of queues, then you need to be careful that you can add in elements just like when you're dealing with stack. But then when you're removing, you're actually removing the leading element, which is really special here. So this is something also you need to think about when you are dealing with live coding part. Okay. But now let's look at the stack that we sort of implement. So okay, so let's look at the code from the notebook. Sharing is not now. The hold is not allowing. I think so let me try reclaiming the host. Interesting. Transcripts, settings. Interesting. Well, let me stop the share from here and let's see what can happen. Sharing is not on. Wait, who is the host? Okay, reclaim. Okay, that's good.
Okay.
So yeah, I was wondering why. Right. Probably accidentally I changed the host of the meeting. So what are we looking at? What are we looking at here? So okay. So in terms of the methods, we are trying to what we are trying to do here is that we of course the underlying data structure we are using are the lists, okay? But remember, we're pushing only at the end of the list, so it's just going to be directly appending that element X, right? So that's easy. But then for pop, we want to make sure that, of course, the list needs to be non-empty so that we can pop something. But then if there is some element, we just remove the last one. Okay, we just remove the last element from the list, and then done. All right. So that's sort of restrictive. So in general, you can remove whatever element that you want from the list. Okay, in the list data structure. But here we just make it a little bit more restrictive. Okay, so only the last one can be removed. So there isn't really a lot of challenge here, so we just need to make sure that it does what we want. So so now let's say we assume we have 1, 2, 3, 4s in the stack. Then essentially, what can be removed? 4 can be removed. Okay, when you add an element, you just add it right after. So 5 needs to, when you call it, it's going to be push. Well, yeah. So just notice this is the function that we wrote. Okay. So when you are calling a function, you just do the way that we usually do outside of the class. So here we're doing it outside of the class. So it's going to be the stack, and we add the element 5 at the end. So that's 5 is that X input right here. But then if we want to formulate it in in a class, it will be just using the dot notation. All right. So, and then, of course, when we're popping the elements, let's try it again. So it's just gonna remove the. All right, just gonna remove the last element, and it just goes on. Right. So it's okay. So now let's look at the implementation of stacks using our class. Okay, we can just define a class. So every class is going to be a subclass of the grand object in our Python language. So just remember, we want to use a list, okay, and we allow adding and removing elements, but it's only the elements at the end of the list, okay. We can pop the thing at the end also. And we want to be able to check whether the stack is empty or not, because of course, if it's empty, then we would prevent from further popping, but because it will give you some bug. We would like also to pick what's the last element without doing anything to it. And of course, you may want to view all the elements. So these are all the attributes that you want to include in the code. And then we're gonna look at here. Okay, so this line looks a little bit different from earlier, right? But it just says what it just says. Now I'm designing a subclass which is called stack out of the grand object in Python. Okay, so the object is the biggest class in Python. And then initialization, what we are gonna just set the attribute that's the elements, the items. Okay, so basically I'm defining the attribute items as a list, okay, as an empty list. And then I just formulate these methods. Okay, so for push, for whatever element that I have, I'm just gonna call the, I'm just gonna call the set the self.items. I'm gonna, okay, I'll try not to highlight that syntax. So I call the list that I defined earlier, and I append the item, right? And then for pop, I'm just gonna still look at the list, and then I pop. Remember, by default, pop is removing the last element if you don't specify the index. Okay, so those are really straightforward. And to check whether the stack is empty or not, once again we're using this kind of lists, okay, as the underlying data structure from Python. So we are able to check whether the length of the list is 0 or not, or we can check whether this list is the empty list or not. Okay. And then picking the last element. So if it's not empty, then we are able to get the last element and then just return it. Okay, so return item. So it's really standard. Just realize that self.items is what? The self.items is the list that you initialize with. Okay. And then finally, this part is what? This part is the string that you print when you try to print an object. So for the object itself, then you would want to here print out the string of this form. Okay, so basically, if you look at the code, this does what? This does the construction of a list that of a string that you print But just remember, you want to print items, right? But you also want to give like a style. So it's going to be the first element, comma, space, the second element, comma, space, all the way down to the last element. But you are only including the separations, okay, from the zeros index all the way to the n minus, let me see, n minus 2 index, okay. So you're not really doing that to the last one. So this is a for loop, but then you add the string for the last element right there. And then possibly you want to sort of emphasize that the beginning and the end of your lists are different. So we are only adding and removing things at the end. So here we have an add symbol to include in the string. So if I try to implement, what does it do? So initially it will begin with an empty list, okay? And then when you push A, it's going to give you an A as the character as the zeros and the zeros index in your list, and then B, and then C, and then now once you do print, that's going to be the way that we defined earlier about that str function. So that string function is the way that you print your current stack, all right? And so the way that we specify is just to sort of indicate that, okay, you can only operate on the end of your stack. So the code here is sort of intuitive, but you're trying to enforce only a few operations that's specified to the data structure here. Any questions? So yeah, let me see what else. All right. So here we are trying to now play with what's called a parentheses problem as an application. So basically, if we go back a little, this how many lines? So the stack class with 1, 2, 3, 4, 5, 6 methods. Okay, we have already everything that we need. So just remember, we have initialization and we have like a print. So we only have like what, 4 methods: pop, remove, pick, and it's empty. Okay, checking whether it's empty or not. So yeah, it's empty is sort of like trivial. So now the parentheses problem. So what does it do? So given a string is containing just the characters, round brackets, curly brackets, and square brackets, we want to determine if the input string is valid. And what do we mean by saying valid? So open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. So it's sort of like, okay, I have a left bracket. I want to enclose it by a right bracket. If I have a left curly bracket, I want to enclose next to it by a right curly bracket. So to close brackets, okay, I wanted to follow this kind of order. So if I do not close it, and then I can always just follow with the left brackets, not the right. Okay, so basically you just need to make it in a reasonable way. So for example, the curly left, round left, square left, and then square right, round right, and curly right. That's valid because if you now look at this pair, that's fine. And then if you sort of like discard that pair and you look at the one on the outside, this is the round brackets, that's fine as a pair. And finally the curly on the most outside, okay, that's fine. But then if you have something like the square left and the round right is not valid since you have different types that are enclosed together. So it's basically when you are given a list of this kind of brackets, okay, you'd want to identify whether this is a valid collection of brackets or not. Okay. And similarly, this one is not. So if you look at the pair, so you actually have three pairs. So it's the square and the square right here. It's the round and round right here. And it's the curly and curly right here. So they are not really enclosing in the correct way. Okay, so this one that you start with by closing it's a square closing a curly. Okay, so that's just makes it not valid. So, and of course, if you have something like this, okay, if you have like a string of text, okay, so if you have a string of numbers combined with other symbols, then this kind of 2 plus 3 multiplying 4 with these kind of setup of brackets, it just looks weird. Okay, so it doesn't make sense. So this is the reason why sometimes people care about this kind of problem, whether the premises in statements are correct or not. But of course, we're not really looking at those kind of general strings. So in general, what can you do for a string of texts and brackets and operations? What you want to do then is to somehow extract all the parentheses out, and then you can uh, sort of reduce the problem that's in our current format. So we just have a string of brackets, and then we want to determine whether the thing is valid or not. Right. Okay, so our solution is to search our string of parentheses from left to right, and whatever we hit the left bracket, we add it to our stack. So those are the left ones. So whenever we see left, we just add it one by one to the stack. And then if we see there's a right bracket that's trying to enclose, right? So then we see, let's say we see a curly, and then we want to check whether the last one in the stack is curly or not. If not, okay, we doomed. It's not valid. If the pair, okay, the last one in the stack and the current one we are trying to close, if they match, then okay, we just remove the last one in the stack, and then we sort of like cancel them out. And then we just continue doing this. Okay, so this is exactly one situation where stack here is nice to enforce. So once we encounter a right bracket, we will compare with the last item in our stack. If they're the same, we will pop our stack. Okay, so the last element is removed, and we just continue comparing with the coming up right brackets. And of course, if there are further more left brackets, we just put them at the end of the stack. Okay, so this is really systematic. Is it clear? So parentheses problem. If the parentheses we're comparing don't match, we know we have an unbalanced pair. Because they have to be closed in the correct order. So wait, this is this. Okay, I think this. Okay, almost the same test. So they have to be the same type. Also, if we pop all of our left brackets and or the balance is off, then we know that there weren't enough pairs to balance our strings. Okay, so if unfortunately you popped out all the things in your stack, and there's still some right parentheses that you want to close with, then it's not possible. Okay, so that's where your balance is off. So just so that gives us sort of like the bottom line. So earlier we have the stack class, then we just need to put that into usage. Okay, so parentheses matching. So of course, the first function that we define here is to match a left bracket with a right bracket. So only when I have square brackets left and right, uh, curly brackets left and right, and round brackets left and right, that will give me a correct match. Otherwise, it will just be incorrect match. Okay, so that's the comparison. Okay, so just remember every time. So for left brackets, I'm gonna keep it in my stack. For the right brackets, I'm gonna use that as B. Okay, I'm gonna use that as B to match with the last element that I pick from my stack. Okay, that's gonna be A. And if is parentheses balanced. Okay, so that's to determine my whether my string is balanced. Okay, so parentheses string is my input, which is a string. So that's the function, that's the main function I'm trying to establish. But here I'm using the stack, right? So here basically I have S to be the left brackets that I store. So that's the stack data type, data structure. All right. So now by default, I'm gonna set the answer to be is balanced. But whenever there's a mismatch, I'm gonna make it false. Okay. So let's see. Index equal to 0. Okay, so index equal to 0 is because I'm essentially doing a while loop. So if you want to do a for loop, then you may do it a little bit differently. But basically, I'm just okay. I'm running through my my string. While the index is less than the length of my string, and while I'm still balanced, okay, while I'm still balanced, I'm gonna move on to the further elements in this in the string. But if it's imbalanced, okay, if now we know it's not valid, then we can stop the while loop. So here I'm gonna each time, okay, capture that character from the string. So now if it's a left bracket, I'm gonna append. Okay, so I'm gonna push it. So of course we are doing we're doing appending, but to be reminded that we are only using the stack class that we defined just now. So we are just using push. Okay, we're just using the push function of our new data structure. Okay, if the element is a left bracket, then I push it to the stack. If otherwise, that means what? That means now I'm going to be looking at a right bracket. So I'm looking at the right bracket. So if my stack is empty, that tells you what? It tells you I have nothing to match with. Then I'm doomed. It's an invalid a string. Okay, so I'm gonna switch to false. All right. But now if there is some element in the stack, then I need to do the comparison now. So it's gonna be I remove the last element. I'm gonna make it at the top. Okay, so that's gonna be the last element in my stack. I'm gonna match it with the parameters that I got. Okay, and if it's a mismatch, if it's a mismatch, is match. So let me make sure. So is match is saying whether these two match or not. Okay, so if they do not match, so let's quickly confirm ourselves. Okay, so yeah, indeed, whenever there's a mismatch, that's gonna return a false, right? But only under that case, that I will be I'll be certain that my string is imbalanced. Okay, so this is why I say it's if not. Okay, if not, is match. So let's just say if not, false, meaning if true, then that tells you okay, indeed there's a mismatch. Indeed there's a mismatch, so that's gonna be a false. And I just do index plus equal to 1. So that's a standard thing for while loop. So the steps here are just saying, okay, I'm running through the list and I'm just trying to find mismatch. So if there's any if there's any left bracket, I'm gonna put it in the stack. If there's any right bracket, I'm just gonna do the comparison. If there's nothing left to compare, then so if there's nothing in my stack that it can be compared, then it's an invalid string. If now everything passes, then it's gonna be a valid string. Okay. So and yeah, in the end, finally, if now S is empty, meaning all the left brackets are handled, but finally it's still balanced, then I know it's a true. Okay. And if the otherwise, either this one is not empty, meaning what? Meaning you have some left brackets that you didn't handle, uh, or if the thing is just it's not balanced from before, then it's gonna be a false. So okay, so let's see. So that looks kind of interesting. So so let's run both of them. So one of them is a little bit shorter, one of them is a bit longer. Okay, so it looks clearly that this one is not valid, right? So I have this pair which is valid, so I sort of can ignore that. And then these two, unfortunately, does not look valid. So then I know for sure this is doomed. So let's run this one and see if it directly, yeah, it gives us what we want. So think about it really systematically. So what have we done? So initially there's nothing in my stack, all right? And then the left bracket will be enclosed in my stack, and the left round bracket will be kept in my stack, right? And then I see the first one is my right round bracket. Okay, so then I have to do the matching. So the round bracket is now matching with the last one in my stack, which is this left bracket. So they are both gone. All right, and then the next element is my curly bracket, and then I'm gonna keep in my stack. And the next step is now where the problem occurs. Okay, so now the square brackets is something we have to match with, but there's nothing to match. Okay, so that's so systematically speaking what's happening. Make sense? Okay, so let's also run the second one, and we're gonna go back to our notes and do a little bit of notes explanation. So this one looks much more complicated because it's longer. Okay, the more premises there are, the longer the more complicated it is. But still, it's true. So let's see from our notes whether we can actually verify everything on it. So only the host can share. Let me change that setting. Share. Wait, it's really weird. Enable control. Let me try it again. Okay, that's the setting. Good. So, okay, we are seeing this this part. Okay. So these are in stacks. Okay, so these left brackets are in stack. And then you are trying to match with these two, and then these two. Okay, so that's where just invalid occurs. Okay, so that's what we were discussing just now. So now let's look at this one. Okay, so let's look at the second example. So we have what we have left bracket. So in the stack, what do we have? So let's just keep the stack, and we are looking for the current. Okay. So what's that variable? That's the parent. Okay, parentheses parent. Okay. So now let me put the stack on the right hand side. This parent is what we can point. So now, firstly, the parameter is this one. So that's going to be our stack element. And then move on. Okay. So now the parentheses is now the square right. Okay. So now we are matching, and indeed there's a match. So this thing is popped, and this thing is handled. All right. Make sense? And then we just move on. Okay. So now it's going to be, let me just move it. Okay, so let me just move it. It's going to be now the round bracket. I'm going to put it in stack on the left. This is the left bracket, and then just continue. The next one is again a round bracket, and the next one is a round bracket. All right. And then the one after is going to be the round, but it's a right bracket. Okay. So that means what? That means we have to match that with the last element in my stack, which fortunately is fine. Okay, so now these are gone. And then the next one is curly and left. Okay, so I'm gonna put it in my stack again. The parentheses, let me switch. I want to switch to the next line. Wait, where is it? Oh, right here. I want to. It's a little bit problematic because every time now I click it, it's gonna give me something I don't want. So I want to slightly adjust. Okay, good. So we are now at the curly. So I recorded this. So move to the next one. It's gonna be a one that I have to match. Okay, so it's the curly. So now again, I'm looking at the last element of my stack and then matching, and then fortunately it matches. Okay, so that matches. That tells you okay, these two are gone, and then move on. So the it's going to be a right bracket. So right bracket is what I try to match. It looks fine, right? So once again, I'm having this one. I'm gonna handle this one. So then I move on. Is the left bracket. What do I do? So now I'm looking at this left bracket, left square bracket. So in the current steps, what should I do? Should I move it to stacks, or should I compare it with something to close? Put it to stack, right? So it's a left. So whatever left that is, it's just gonna be in the stack. So then we move on. So what do we do now? Compare with the last element in the stack, because we want to close it. So I did this so that matches good. And then we have the last one. So the last element in my string is a right. So again, I try to close it. Okay. So there's only one element in the stack. So once that's verified, I'm done. I'm completely done. So indeed, there's nothing in my stack anymore, and there's nothing to be handled. So currently, we didn't rewrite the if balance Boolean variable. So where are we? We are actually here. Okay, so once we run through everything, we finish the while loop. So now we finally need to check these 4 lines. So now S is empty. Okay, so that's true. And is balanced, that's also is balanced. It's not modified. Okay, so by default, it's true. So there's no mismatch, so it's still true. So we return true right here. Okay. But if there were any mismatch, then it's going to give you a false right here. So that will give you false. Or if the thing is not empty, okay, if there's anything that's not matched in the stack, then we have this one to be false. Then that means it's not, we went through the entire list. We went through the entire stream, but there are certain lab brackets that are not handled. So in that situation, it's still going to be imbalanced. So that's good. All right. So yeah, indeed. So this tells you indeed there are certain tasks we are able to efficiently utilize our stack data structure, okay, to handle it. All right. So that's stacks. Okay, queues. So just remember, like in the diagram there, it's going to be first in, first out. So meaning what? Meaning we have a list from, let's say, 0, 0, 1, 2, 3, 4, 5, 6, all the way down to n. So we can remove the zeros element. We can add in the n plus first element. So there are both reactions that we need to handle. So that's a little bit more interesting. Okay, so these are the methods that are called NQ and DQ. So these are the insertion and removal. So we need to treat it a little bit more carefully. So so here now we're gonna jump into live coding. Okay, so for practice problems of lecture 8, so essentially we now notice that the stack as a class is actually sort of not really difficult to implement, and we just need to modify the code a little, okay, for queues. So just remember, for queues, we need to get the method, okay, enqueue. It's just adding items, okay, to the end, okay, of queue. Okay, to the end of queue. When you dequeue, you remove the first element. Okay, so remove the first element in the queue. And then, of course, front and rear, that's just calling the elements, just not really modifying the elements. Okay, is empty is the same from before. So also make sure that's actually a print. So this is a print that are modified in the later versions of the Jupyter notes, but currently this should be a print. So just make sure that you know how to use the underscore string str function to somehow print out your results. All right. So a second part of the question is that here, notice this is something we want to do carefully. So we know that the only difference between a stack and a queue is that the stack is last in, first out, but then queue is first in, first out. Okay. So with this information, create a class that's called stack, but now we're utilizing 2 queues objects. Okay. So this is not implementing the stacks that we just wrote. Okay. It was in the earlier we wrote stacks using what's that term? Using lists. Okay. So but here we are only using queues. So what we want to do is utilize the add and remove using the first in, first out. Where is it? Make an object that takes in elements and pop elements LIFO using only two of your queues. And so notice we use two queues and NQ and DQ methods. Okay, so that's something we're gonna play with in the live coding session. And yeah, you guys can continue with the live coding session here. So, oh, interesting. So any questions that you have for the live session? I think lecture 7 we finished. I think we finished it. Well, of course, much of the things are related to homework, right? But of course, make sure to continue with that. So the code. Let me get to level 2, lecture 8. So yeah, indeed, in this one, make sure to play with the initialization, the string function, the less than function. Question 1. Yeah, question 1 and question 2, they're sort of like a continuation from before. Question 2 is okay. Question 2 is definitely related to today's class. It's the lesson function and the string function there. Okay, that you can write. And then question 3 here is saying, okay, I have like a inheritance. Okay, I have a subclass that's called the lake house. So earlier we have the number of units, right? We have the number of floors. But here for lake house, it's going to be a default number of units that you need to always use as 1. And then we have additional attributes that get both status and whether the lake house is rented or not. Okay, so these are certain special things that you want to use inheritance. Okay, so just remember how to initialize your subclass. Okay, just it's partially calling the initialization of the superclass, but also introduce more attributes there. So just be reminded that Wednesday we have a quiz, and the rest of the class will continuing with the live coding.
Is the quiz on lecture 8 and 7? Or part of lecture 8?
Mostly the things before lecture 8. So but indeed we will have some OOP questions, just a little bit more fundamental.
Okay.
Yeah. So yeah, let me stop recording as the class is over.
Thank you, Professor.
Yeah, no problem.